In the context of navigation, most commonly used methods are model-based, which are frequently good in practice, but can be tricky to configure and cannot be adapted based on a robot's own experiences. Imitation learning can be a suitable alternative to traditional methods, as it allows a robot to acquire execution policies by being trained or adapted based on expert demonstrations. Nevertheless, studies focusing on learning-based methods typically do not make an attempt to directly compare learned policies with traditional methods. Because of this, the benefits of learning-based methods are sometimes not clearly visible. Particularly, the effect of different modalities on a robot's navigation performance can be important for informing the decision about whether a learning-based approach may be sufficient in a given context. In this paper, we analyze these aspects by considering a mobile navigation platform equipped with a 2D laser scanner and an RGBD camera, such that the goal is to navigate in a university indoor environment. In this work, we use behavior cloning to train a robot navigation policy based on expert demonstrations. We concretely train goal-conditioned network-based policies for local motion planning. This combines sensor data and a goal representation to produce velocity commands for planar navigation. We train three types of policies with different sensory modalities, such that features extracted from both sensor data and goal information are used as inputs to the policy networks. The simplest model only uses laser scan data for navigation. Our second model uses only image data for navigation, and the final model we investigate is multimodal, namely it combines both image and laser data. In our evaluation, we compare these methods with a potential field-based method for local motion planning. We perform the evaluation on 4 indoor navigation scenarios, which are illustrated here. Straight line navigation, corner turning, navigation in a confined space, and navigation in a space where a dynamic obstacle appears. The shown plots illustrate the results of the comparison. We can particularly see that the image-based model performs the worst among the methods in terms of success rate, while the multimodal model is the best learning-based model, with performance comparable to that of the potential field method. Dynamic obstacles are, however, problematic for our learning-based policies. To demonstrate the ability to use a learning-based policy in a complete navigation framework, we also integrate a learned policy with an A-star path planner. This plot is an example of using the laser-based policy to follow a path plan to a given goal. In this case, the robot eventually drifts away from its path. In future work, we would like to address various problems with the learning-based policy. First of all, we could try using data that includes dynamic obstacles to train a richer policy that can deal with such cases better. In this work, we only used the latest sensor measurements as input to the policies, but we could also try to include some history by including temporal information and using a transformer-based policy. Finally, we would also like to investigate the integration of our imitation-based policy with subsequent reinforcement learning or lifelong learning in order to enable continual adaptation.